Alright guys, let's talk about lesson 3, which is potential energy diagrams. Potential energy diagrams show the change in potential or stored energy during a chemical reaction. So if we look at this diagram, potential energy increases as we go up the y-axis, and the reaction progress increases as we go across the x-axis. So if we were to read this graph, potential energy is the same, then it increases to a peak, and then comes down, and then levels off. So there's different types of potential energy diagrams. So the first one is an exothermic potential energy diagram. So that is when the product side is lower than the reactant side. And the reason why this happens is because energy is released as a product, so the net amount of potential energy is going to decrease. And so that means your delta H is going to be negative. So if we look at this, since our products are lower than our reactants over here, this is going to have a negative value, and so our delta H is going to be negative. That energy is the part that's released, that difference between our reactants and our products, and that is a negative value. So endothermic, the product side is higher than the reactant side, and that's because energy is absorbed by the reactants, so the net amount of the potential energy increases. That's because the delta H value is going to be positive. And so if we look at a graph and we look at that potential energy difference, that is what is being absorbed, so that's why it's a positive value. So there are different parts of the potential energy diagrams. You must be able to label these, so the diagrams in your notes as we go through this. So let's look at activation energy. Activation energy is the minimum energy required for a reaction to occur. It's the energy needed to get over that hill. That's your activation energy. So right here would be our activation energy. Okay, what we're going to do right now is we're going to watch a little YouTube video that's going to explain activation energy.
If oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
Okay, so that little video explains what activation energy is. So an activated complex is the highest energy point of the reaction. It's temporary, and that's where the bonds are broken and bonds are formed. The heat of reactants and products is the amount of potential energy possessed by the reactants and the products. And the delta H of the reaction is the amount of energy lost or gained in the reaction, and it's subtracted for the heat of the products minus the heat of the reactants. So whatever energy is down here minus whatever energy is up here, and that's what you will get for your delta H. Okay, so let's look at the effects of adding a catalyst. It lowers the activation energy needed to start the reaction, and the reaction occurs faster. So think about it like this. If you have a reaction and you don't have a catalyst, you're going to have to put more energy, more work to get the object where you want it to, or in this case, to get this reaction to happen. If you have a catalyst, it takes less energy, so the hump needed is going to be less. So let's look at a practice problem. Is this an endothermic or exothermic reaction, and how do you know? Pause the video, unpause when you're ready. Great, well, welcome back. This is going to be an endothermic process because, as you notice, the products are higher than the reactants, so heat is absorbed. Which arrow represents the activation energy for the reactants? Pause the video, unpause when you're ready. Great, welcome back. You should have said that B. B is the activation energy. The activation energy is the energy from the reactants to the top of the peak. Check your understanding. This is what we're going to answer first thing tomorrow in class. Is the delta H positive or negative for this reaction? Have a good night.